In this video, I'm going to do a non-standard minimization problem. So we want to minimize c equals 5x plus 2y subject to these three constraints. Now you'll notice that we have mixed constraints. The first inequality is a less than or equal to. The second inequality is greater than or equal to, and the third is also greater than or equal to. This makes it mixed constraints because some of them are less than or equal to, some of them are greater than or equal to. So because we have a minimization with mixed constraints, it makes it a non-standard minimization problem. So the way that we solve a non-standard minimization problem is actually quite simple. We simply change the minimization problem to a maximization problem. And we keep the constraints exactly the same. We do not change any of the constraints. So what this means is we are going to change minimize c equals 5x plus 2y to maximize p equals negative 5x minus 2y. So all we do is we change the sign of the terms on the right-hand side of the objective function, and of course change the c to a p to represent the fact that we are maximizing. The constraints, as I already said, stay exactly the same. So now we have a non-standard maximization problem, which we already learned how to solve. So the first step is to create our system of equations. And so we start with the first constraint, 2x plus y. And so we have a less than or equal to sign. And that means that we are going to have to add a slack variable. In the second inequality, because it is a greater than or equal to sign, we have to subtract a surplus variable. And in the third, we also have a greater than or equal to, so we subtract another surplus variable. And then we take our objective function, which is now negative 5x minus 2y. We take those terms and we subtract them over to the left-hand side like we always do. And so we end up with 5x plus 2y plus p equals 0. So once we have our system of equations, we create our initial table from that. And so we have an x column. And so in the x column, we fill in the coefficients from our equations. The y column, r, s, t, p, and c. Now, it's real important to make sure that you don't forget that this is negative and this is negative. And so once we have our table, we have to determine which of the active variables are negative. Well, in the initial table, because we have a negative s and we have a negative t up here, and this is negative and this is negative, that means that s and t are going to be negative active variables. And so we highlight those two rows, the S row and the T row. And so in the initial table, even though we have all positive numbers in the bottom row, the initial table with mixed constraints never represents the solution because we're not even in the feasible region yet. And so what we need to do is to get into the feasible region. And that's what this phase one that we learned about is. In phase one, we are attempting to get to the feasible region. Once we get to phase two, we are in the feasible region and we're moving around the feasible region looking for the optimal solution. So in phase one, we go to either one of our rows that are highlighted. That would be the S row or the T row. And I chose to use the T row. And we look for the most positive number in that row, which was 8. And so I chose the X column then is my pivot column. And then we just look at the ratios. Take the ratio of 6 to 2, 10 to 2, which is 5, and then 16 to 8. And so 8 ends up being our pivot because 16 divided by 8 is 2, which is the smallest ratio. So 8 is the pivot. And so now what we need to do is we need to clear the pivot row. And to clear the pivot row, we use our normal row operations to get all zeros, except for the 8, all zeros in the X column. And so to do that, we use row operations. So the row operations I used are over here. So to clear the first row, I did 4 row 1 minus row 3. To clear the second row, I did 4 row 2 minus row 3. And to clear the fourth row, I used 8 row 4 minus 5 row 3. And this is our new table. And so you can go back and actually use these row operations to perform it, and you should get these numbers. So now the question is, do we have any negative active variables? And so we do. If we take a look at the R, how do we determine if R is negative? Well, we take a look at the constant and we divide it by the number in the R column and the R row. Well, 8 and 4 are both positive, so that's going to be a positive number. S, we got a positive 24. Oops, divided by a negative 4. That's going to give me a negative active variable. 24 divided by negative 4 is a negative 6. So S is a negative active variable, so I highlight that. X, well, we take 16 and divide it by a positive 8. Well, that's going to be positive. So we only have one negative active variable now, and that's the S. So we are still in phase 1 because we have a negative active variable. We are not in the feasible region yet. And so what we want to do is go to the S row and look for the most positive number, which is the 18. That makes the Y column my pivot column. And then we look for the positive number with the smallest ratio in that column, and it turns out to be the 18. And so 18 is the pivot. So once again, we want to clear the pivot column of everything except the 18. And so I did that to obtain the next table. So I did 9 row 1 minus row 2 to clear row 1. I did 9 row 3 minus row 2 to clear row 3. And it looks like 3 row 4 minus row 2 to clear row 4. And so we end up with this new table. And so we want to determine if we have any negative active variables. So R, we would take a look at this divided by this, it's positive. Y, this divided by this is positive. X, the constant divided by X is positive. So all of our active variables are positive, so we are done with phase 1. We are now in the feasible region, and so we can start phase 2. Well, as it turns out, we are done because the bottom row has all positive numbers or 0. So as soon as we got into the feasible region, we were at the point that represents our optimal solution. So to determine the solutions, we do that like we always do. The X value is 120, which is the 120 divided by the 72, which is 1.6666, which is 1.6 repeating. Y is the 24 divided by 18, which is 1.3 repeating. And then P is the negative 264 divided by 24, which gives us negative 11. That means the optimal solution to this is a negative 11. Now, this is what we just solved was a maximization problem. We just solved a non-standard maximization problem. But in linear programming, it just so happens that the solution to the non-standard maximization problem and the non-standard minimization problem will be the same. So that means our optimal solution is -11, and it occurs when x is 1.6 repeating and 1.3 repeating for y. All right. I hope this video was helpful.